Okay, welcome back. What I want to do is to continue with NVQ level 3, okay? And again, we're looking at level 3 NVQ diploma in installing electrotechnical systems and equipment, building structures and the environment, unit 304. Now there is quite a number of units to the 304, okay? Sorry, let me rephrase that. There's quite a number of sessions to the unit 304. And that's your EAL reference number as well. Okay. Now, let me just go in here. Okay, bringing in session 6. So we're on session 6. Okay, session 6 earthing. Okay. And here's all learning outcomes. Okay, learning outcomes. The student will be able to gain a deeper understanding of earthing, calculate the size of protective conductors. Okay. Now again, use your on-site guide because the on-site guide gives good examples of calculations for these. Okay. Let's come down into the light. And you can see here we have protective devices. Okay. Go back up again and bring this into play. Okay, bear with me. Make sure that just want to make sure I get everything into frame. Okay. We'll pan back shortly. Right, regulations 411. I will just refer to regulation 411. You could read the rest for yourself. Okay. But it is regulation 411.3.2.1. Now again, there may have been some changes in regards to the 18th edition. Okay, but the last time I looked, they were still the same reference numbers. Requires that a protective device must automatically operate within the disconnection times provided by regulation 411, etc., etc. Regulation 411, etc., etc., and regulation 411 again, etc., etc. You can read that for yourself. Okay. I've gone in closer so you can read and see the regulation which needs to be complied with. Okay, for circuits rated not greater than 32 amps, the standard details the maximum disconnection times in table 4 to 1.1. Now you need to look at this table because it is located in the IE regs, and I think there's a brief account of it in your on-site guide. Now let me just come back a bit, make sure we can get everything into view. Okay, go a little bit. Okay. Now you can see here that system, TN system, 50 volts to 120 volts, AC is 0.8 seconds. Your protective device must operate within 0.8 seconds or less. 120 volts, and if it's a TT system, you must operate within 0.3 seconds. So with your TT system, you need to make sure that your electrodes in the ground provide a low enough resistance to operate your protective device within the given time. Okay, so you need to make sure that your TT earthing electrodes are effective. Now 220 volts to 230 volts AC, 0.4 seconds. TN systems. TT systems, 0.2 seconds. Okay. As you can see here, as the voltage increases, the time of operation reduces. So your device at a higher voltage needs to operate faster. 230 volts to 400 volts, TN system 0.2 seconds, TC system 0.07 seconds. Okay, and again up and above 400 volts 0.04 seconds. Okay, now again read this for yourself, look at the tables in the reference to the regulations here given here. Okay, so forth. Get familiar to bear in mind you're given tables, look at those. Okay. The note in the standard deals with situations where disconnection may not being required for one reason but required for another, such as protection against thermal effects. Okay. Let's pan back, make sure we get everything in. Okay. Okay, thank you. Now for circuits exceeding 32 amps. Okay. Let me just pan in here for you so you can see it for yourself, okay, and read it as well for yourself. Okay, I don't need to read this out to you all the time, okay, because you can read effectively. Okay, but what I will do is illiterate what is being said and what is being shown. Okay. Let's just get it all in. Come back a bit more. Okay. Now, circuits exceeding 32 amps, distribution circuits, and circuits exceeding 32 amps for TN systems can have a maximum disconnection time of 5 seconds. And it tells you which regulations to look at, 411.3.2.3. Similarly, for a TT system, the maximum disconnection time is 1 second. And again, it gives you the relevant regulations which you can need to look up and refer to. Where it is not possible to achieve the appropriate disconnection time, regulations 411, etc. permits supplementary equipotential bonding to be installed in accordance with regulations 415.2. And again, if you look up in the IE regs, it will tell you and show you where the regs is located. Now, if you look up for 415.2, you'll find that the numbers are quite large and you shouldn't have a problem finding this. But you need to take your time, read through the IE regs, look in the index, look in the reference pages and use those. Also use the on-site guide, because then that guides you to a specific page within the IEE regs. Okay. Earth fault loop. Okay. Again, we've done this already previously, and it's a continuation. It crops up all the time. Okay. It doesn't go away. It's to make sure that you understand the relevance and the importance of the earth fault loop. The earth fault loop consists of the point of fault having a negligible impedance, the circuit protective conductor, the main earth terminal, the earthing conductor, the distributor's earth or the general mass of earth, the distributor's transformer winding, the distributed line conductor, the line conductor in the installation. Okay, and I'm just going close for you so you can see this for yourself. Okay. Now I'm not going to go over this too much because you can see here ZE, R1 and R2. Okay. Consumer supply intake point. Okay. R1 is your live conductor, R2 is the earth. Okay, so it's the potential difference with adding R1 and R2 together. That gives you your relevant and total values. Let me just go in close so you can see this. Okay, let me just bring it down a bit. Okay. Okay. Now you've seen this already, for loop. Okay, it's occurred in a number of occasions, so you should not be familiar with this by now. Okay, so let me go back up now a little bit. Okay. Now the earth for loop has an impedance value. Okay, the resistance of the conductors, the reactance, the effect of capacitance on or inductance in an AC supply of the conductors, the resistance of the transformer windings, and the reactance of the transformer windings, S. Now R1 and R2 plays a very important part because you need to know the value of the R1 and you need to know the value of R2. Okay? And what you're looking for is a very low impedance, so that if there's a fault occurs, that it will trip your protective device. That is what this is about, to make sure that your protective device will operate effectively and in the given time. Okay, let me just go up a little bit to make sure that we got everything in. Okay, good. Okay, everything is in. Let me just pan back so we can make sure it's in line. Camera seen. Okay, thank you. And here we have earth fault loop impedance. Now let me just pan into this so we can see it in full before I go any further. Okay, I'm just going to pan across so you can see it and read it, okay, for yourselves. Now again, here I don't need to read this to you. You can see this for yourself and read it for yourselves. Okay, but you need to make sure that you read it. Don't just think you can just glance through it. That's not going to work, because the regulations is specific, and you need to know which regulations you are referring to. Okay, the protective device of a circuit must be designed so that it will operate within the time required on the regulations, etc. And the regulations is for 11.3.2. And again, you can read this for yourselves. The part of Earth fault loop that you are generally directly responsible for are the final circuits, and in particular, the sizing of the protective conductors. So you have your supply here, distributors line, distributors earth, consumer line, consumer's earth, R1, R2, and earth, whatever that might occur there. Okay. Now this is just a hypothetical fault should a fault occur. Okay. That would normally be your appliance or your item system, which if you look back at the earth fault loop, that is a prime example what this would be representing. Okay. Okay, let me just kind of okay. Back a bit. Thank you. Bring it back into frame. Okay, thank you. Okay. I hope you find this bit useful. And here we have looking at incorrectly sized protective conductor. Now, when there is a line earth fault, a large amount of current flows. Should an incorrectly sized protective conductor be chosen, then the fault current may not be large enough to cause the protective device to operate as quickly as it should. The protective conductor may also melt should too much current flow for too long a period of time. Okay. So it is essential that the right circuit protective conductor is chosen. The speed with which the protective device operates is also important. The greater the current, the quicker the protective device will operate, and the less heat is generated within the conductor. The maximum permitted values of earth loop impedance for a range of protective devices are listed in table 41.2, 41.3 and 41.4. Now again, check that these tables exist in the 18th edition of the IEE regs or IET regs, okay? And that they are the same. The last time I checked, yes, they were, but don't hold me to that. Things changes, and you need to take into account those changes to make sure you are concurrent with current practice in your time. Now these values can also be calculated from data in Appendix 3 and be gained from the manufacturer of the protective devices. Okay. I'm just making sure it can be seen and be read by yourselves, okay, and that you know which regulations it is referring to. Okay. Okay, thank you. here we have correct sizing of protective conductor. It matters, okay? The correct sizing of a circuit protective conductor requires some careful thought. There are two aspects, as we have already seen: to determine whether the protective device will operate within the time required, and to determine whether the thermal constraints of the conductor are met. Will it withstand the current load? To size the protective conductor, we make use of standard data listed in tables found in the on-site guide published by IET. Okay, make sure we have this in view. Okay. Okay. Determining cable sizing. Okay, let me just bring that down, make sure. Okay, determining cable sizing. Okay, determining cable sizes using a water heater as an example. Now, a water heater is protected by a 30 amp BS3036 fuse. The length of one is 24 meters and the circuit is wired in length of one is 24 meters and the circuit is wired in 4 2.5 millimeters twin and earth cable. The external earth fault loop impedance has been measured and is 0.19. Now notice you've been given the external fault loop impedance, okay? 0.19. The supply voltage is 230 volts, so you have your supply voltage. Determine whether the Cpc is large enough. Voltage equals 0.230 volts, Z equals 0.19 ohms. Fuse, okay. And 2.5 millimeters square. Okay, so let's go down to this diagram so we can make sure we get the diagram in full. Okay. Now I have to question this a little bit here, okay? You have to excuse me for a bit, but here is 24. The one is 24 meters, and the circuit is wired in 4 2.5 millimeters square twin and earth cable. Now there's a reading here that doesn't seem to make sense in my mind, okay? Okay, because the water heater could be wired as it does tell us it is 30 amps, yes. Okay. Okay. It's okay, we're just looking at something here that adding up in my head, and the 4 here gives me a little question mark at the moment, but maybe I'm looking at something else, or thinking about something else, which is possible in my case. Okay. So we're determining whether the Cpc is large enough. Now here, this gives me a question again, whether it's 4 millimeters or 2.5 millimeters. And we know it's 24 meters one. Okay, so again, it's a little question for myself. But again, look in your on-site guide. Look at the IET regs, make sure you understand the concept as to what this is referring to, and that you can eliminate any errors that you may see here. Okay, because the on-site guide will give you a working example as to what should and should not be. Use it. Right, here we are. Okay, let's see if this will now tell me what my concerns were. I think we'll rectify it. Determine the total impedance of the circuit. Okay, so let me just pan back a bit, then I'll go in closer. To determine the value of the resistance of the line conductor R1 and the circuit protective conductor R2, we have to use data on the specific resistance for different sizes of conductor. Using the on-site guide, table I1 details the resistance per meter, ohms per meter of different sizes of conductor. Table I3 details correction factors for temperature. In this case, the correction factor we would use is 1.2, and when you look in your on-site guide, it actually gives you this figure 1.2. But for some reason, I may be considering this being a change to this in the new regs, but don't hold me to it. Check it, check it, check it. Okay, this allows for an increase in temperature from the assumed starting point of 20 degrees Celsius, the listed temperature, and an assumed normal operating temperature of 70 degrees Celsius for the cable. From table I1 OSG, for 2.5 millimeter cable equals R1 plus R2 equals 12.02 ohms per meter. To find the total earth impedance of the circuit, ZS equals ZE plus R1 plus R2. For ZE, contact local supplier. Okay? But we've been given ZE already, because in the previous question, when we go back to it, it told us where that ZE was. Let me just make sure that I've got the right one. It told us that ZE was 0.19, and here's 0.19. So we know what ZE is. The external fault loop impedance has been measured and is 0.19. Okay, let's go back. Okay, so here now we have R1 equals R2 times I times F. R1 equals 12.02 times 10 to the minus 3 times 24 times 1.2 equals 0.3462 ohms. ZS equals ZE plus R1 R2. So we know ZS, we know what ZE is, we've been given it, 0.19. We know what R1 R2 is, 0.3462. Total resistance equals for ZS is 0.5362 ohms. Now, will that be good enough? That is the question. Okay. So let me just go into this now and get this down to you. So let's go in and going into it, panning in so you can see it and read it for yourselves. Okay. Panning back. Okay. Okay, panning back. Okay. Okay, and let me just go up to make sure we now can get all this in. Okay. Now you need to write out these examples for yourself and use the on-site guide. And you look up for the table. It will tell you in the index. You cannot miss it. Now you have to apply some work for yourselves. Okay. It means you have to do a bit of work for yourself. Some of you seem to like you just want it done on a plate for you. It's not going to work that way. Okay. Okay, thank you. Let's have a look now. So now for 2, let me just drop this down a bit. Okay. Should be in that. Okay, drop this down into center. Okay. Now for 2, determine the fault current level. IF equals V over ZS. Z being the impedance in regards to the resistance of the R1 and R2, which we have just calculated previously. Okay, so we now know that IF equals, the fault current will be 429 amps. It is not necessary to be accurate to any decimal places. Okay, 429 amps will suffice. Now make sure that you've calculated this on your own calculator for yourselves. That it does come up to 429 amps. Okay. One of the things that some of these things can do is give you wrong information, or the calculation wasn't done correctly. So check it, check it, check it. Five, 3, 6, 2 equals 428.9, but yes, it will be 429 amps. Okay. That is good. Okay. Okay. Good. Thank you. Now 3, check shock protection from appendix 3 graphs. Okay. This now means simply that which cable will give us the time operation, and will handle the amount of current that has to flow in order to fit that device. Okay, so here we are looking at check shock protection and appendix 3 graph. Using appendix 3 of BS7671, you will see the graph detailing the time current characteristics of BS3036 fuses. The horizontal axis represents the fault current. The vertical axis represents the time. If you look along the horizontal axis of the curves for BS3036 devices, for the 30 amp fuses, you will see that 429 amps represents a time of approximately 0.11 seconds on the vertical axis. We can therefore safely say that shock protection has been achieved. In reality, we only needed to operate within 0.4 seconds. Okay, but in this case, it's operating a bit faster. So we are within our time, and the faster it operates, the more protective our circuit will be. Okay. Let's go ahead and pan this for you so you can read this for yourselves. Okay. Okay, now pan out, so we make sure we get it all in. Okay. Okay. And yes, we have it all in. Okay, good. So here is our operating time within standard format. 0.4 seconds we need to operate it in, and it's operating in 0.11 seconds, so we are well within our criteria. Okay. Now write these out for yourself. Look and read the information. Now checking for thermal constraint. Now using regulation 543, etc., etc., we need to consider the adiabatic equation and the various K factors that apply to cables found in table 54.2 to 54.6. The K factor takes into account a wide range of factors regarding insulation, temperature change, conductor material, etc. The K value should merely be used as a simple multiplier cum divider. Using the example, using table 54.3 as the cable is thermoplastic, insulated and sheatheded twin and earth, the value for K is 115. Now if you look in your tables, you may find that this 115 may change. It may have gone up or it may have gone down because the measurements is taken as a given value at a given point in time, and other materials comes into play which creates a better effect in some cases. So be aware that this figure here, K value, may change. Okay. When I looked at it last year, 2019, this, I believe, that value here has slightly changed. Can't remember what it had changed to, but in regards to the 18th edition IE regs, it had, and a new on-site guide as well. So use your on-site guide. Okay. Now here you have your formula. S equals I squared times T over K squared, square root of. S equals, we know that 429 amps was given in a question earlier, and you'll need to look back at that yourselves. Okay, so let me just recap for you. Okay, so let's go back a little bit, and you will see that it was given in your previous information, 429 amps, and you see it here. Okay, 429 amps. Okay, and we have a time of 0.11. Now the thermal constraint is in respect of your K values, to keep that in mind. Okay, when you're talking about thermal constraint, that is your formula for your thermal constraint situations. Now 429 times 0.11, divided by 115 gives you 1.24 millimeters. So what we're saying here is that as the Cpc is 2.5 millimeters squared, it is therefore perfectly acceptable. So you can see that here we're looking for, will the conductor handle the earthing, the amount of current to be carried? And we know here that 1.24 millimeters will handle the current of 429 amps. But as we have got the Cpc is 2.5 millimeters, it is therefore perfectly acceptable for the current carrying capacity and in regards of all thermal constraints. Okay, so our thermal constraint has been met in respect of the value of the earthing conductor size. Okay, let me just go in a little bit. Did I? Okay. Okay, let's pan you in. Okay. Now you need to read this for yourselves, okay? And bring it into play at all times. Okay, that's good. Thank you. Now remember to write this out for yourself, especially these equations. Get to know them. You have to use them. Okay. Terminate the side of the Cpc. There are 4 steps in the termination of the side of the Cpc. Briefly, these are. Oh, sorry. We'll bring that down. Terminate the side of the Cpc. Okay. Yeah. Thank you. Okay. Let's get that next screen. It's okay. I was a little bit wide. Thank you. Okay. That's better. Okay. Briefly, these are determine the total earth fault impedance, determine the earth fault current, determine the time taken for the particular device to operate, determine the thermal constraint based on regulations 543.1.3, allowing for any change in these regulations due to any new additions in regards to the 18th edition or thereafter. Okay. Multiple choice questions. Okay. Now please answer the questions. Okay. And again, answer the question for me, please, okay? Okay. Answer the questions, do the questions. It enables your understanding to take place, okay? And it allows your brain to concentrate on what is relevant and important, okay? Just check there's nothing further on there. Okay, that's good. Okay, thank you. Okay. Okay, that will be us. Thank you. I will stop there now. And I hope you would have found this useful. Okay.